very happy to be here. Get caught up with Lou. Lou and I went to high school together, so we haven't seen each other. Yeah, we haven't seen each other in, so let's see, about 45 years approximately, so that's interesting. But Denise asked me to talk about the biological attributes of the wood Pawcatuck Watershed, and it's way too much to talk about, so I'm going to show you some patterns. I could sit here and talk about, show pictures of animals and stuff, and bore you to death, but I want to show you some bigger patterns. So with that, this is my impromptu title for this talk. Now, to start with the wood Pawcatuck Watershed, we have to take a trip back to the Stone Age, because everything that's present now is a function of things that happened 20,000 years ago. So I know this is not, you never apologize for your graphics, but I know this is a little not totally intuitive. But these four panels show what the landscape of this area looked like at different points in the past. The 12Ks are 12,000 years before present, 9,000 years basically ago, 7,000 years ago, and 6,000 years ago. Now, you're all familiar with glacial history, I'm sure, to the point where you understand that around 20,000 years ago, Rhode Island was under about a mile of ice. And so at that point, the glacial margin was out here by Block Island. The light gray was exposed shoreline, because when the glacier locked up all the water in the planet, the ocean dropped about 300 feet because all the water was in ice. Now, as the glacier got to about this point, after a few thousand years, it started to recede. And as it did so, the water went back into the sea and the ocean began to rise. It wasn't a straight relationship, because as the ocean was rising, the land was also rising, because when the ice melted, it took the weight off the land, so the land was also rising in a process that's called isostatic rebound. So that basically, over time, the ocean caught up with the land and brought us to this current position. The reason that this is important is there wasn't anything here at that time. There was nothing living under the sheet of ice. So the animals and plants, in large part, that we have here now is a function of those that were able to get here following glaciation. And given that this was all ice, most animals were displaced and plants were displaced southward. And as the land became exposed again, they began to move to the north and eventually recolonize New England. These yellow arrows show a couple of the pathways that they took. Animals, like people, are basically lazy, and they take the path of least resistance, which means that river valleys at low points in the landscape were natural corridors for northward expansion. A lot of animals came up the coastal plain, flat land up here, come up the Connecticut River was a big corridor, and across the Rhode Island coastline. Another pathway led to Long Island. And then another one, there's a big valley here which leads up to Albany. So you can still see relics of these pathways on the landscape if you look at the present distribution of species. And to illustrate this, I want to talk about freshwater mussels, which are depicted on the left. We have about 10, we don't have a terribly diverse fauna. We have about 10 species of freshwater mussels. And the reason the mussels are interesting, I'm going to talk about these two here, eastern pond mussel and lamp mussel, is that mussels, as you can probably imagine, don't travel that great. If you're an aquatic organism and you can't fly, you have a hard time getting from watershed to watershed. So if you're a bird and you see this exposed coastal plain, you go, whoa, that looks great, and you just fly over there. The mussels and other animals that travel very slowly took thousands and thousands of years to recolonize Rhode Island. Mussels have a particularly hard time at this because they have I'm a little nervous, have a really complicated life history that involves, mussels are symbiotic with fish. Part of their life history involves the larvae actually attaching to fish. And they spend part of their life history attached to the gills of fish, and then they drop off and form your classic mussel that has the shell. So fish are a little bit better dispersed than mussels are, but either way, if you're a fish or an aquatic organism, like I said before, and you can't fly, you have a hard time colonizing the coastal plain. Many of these species were very, very slow to arrive in this area post-glacially. This map shows a composite range map of those two species I had images of before. And you can see that they're found almost exclusively in two drainages. And this is because, I think, that this was a major post-glacial corridor into the state. This is our favorite watershed here. Of course, and the Pawtuxet is also another one, particularly the south branch of the Pawtuxet seems to have more aquatic biodiversity. And many of the other drainages in the state, which are, except for the Blackstone, are pretty minor drainages, don't have these species at all. So what I infer from this, this pattern, by the way, also repeats with plants, reptiles, amphibians. A lot of different animals show the same pattern, localized in this watershed, maybe this watershed and not found elsewhere. So what I would say in this, what I would infer from this, is that most of the, what I would call the ancestral biodiversity, that is the most stuff that got here post-glacially, is right in there. So there you go. So obviously, if from my perspective, I'm charged with protecting the biodiversity of the state. I'm not here to talk about public recreation or kayaking or anything. If you want to protect the biodiversity of the state, that is, maintain habitats and species, the full complement of stuff we have, you need to focus on this area. So I'm going to do a little different. I'm going to do three sorts of lines of inquiry here. Another group that I'm pretty much interested in is reptiles and amphibians, like these newts. And I've done an extensive amount of sampling for reptiles and amphibians, and what I find is a different sort of pattern that repeats itself. So we start off with the ancestral diversity. So 10,000 years ago, 5,000 years ago, there was stuff here. Since that time, particularly since colonial occupation, or whatever you want to call it, a lot has happened to those species, and a lot has happened to the landscape. And this pattern is a pattern that happens a lot with amphibians and other species, whereby it's absent from urbanized areas. Well, it's not a big surprise that, you know, salamanders don't like concrete. But what is interesting is that even where there are habitats that persist within these sort of the urbanized, the greater metropolitan area, habitats that would seem to support these species were they in a different part of the state, they're still absent. And I think the best way to explain this is just basically by looking at the road density, because the road density is a very strong predictor of what your terrestrial vertebrate population is going to be, because animals, like people, don't like getting run over by cars very much. So what's happening here, I think, is that as these, and this is not the only urban area, as these urban areas expand outward, you get this sort of, it's not a fixed line like this, like I've shown it, but you basically have a loss of biodiversity that extends outward from urban centers. And so if you extend all the urban centers, including Westerly, South Kingston, whatever you want to look at here, what happens is you end up right in here, the same circle that I could have drawn before. So one way to look at this, all I did here was just take the road map in a GIS cover, and I just buffered it by a certain an arbitrary value, with the assumption that a road and the land proximal to it, that is next to it, is not going to be able to support a lot of wildlife, or at least not the full complement of wildlife. So one way to look at that from the negative is to take the roads and buffer them and see what's left. So if you buffer all the roads in Rhode Island, there's the roads that bear traffic, and you put a 1 kilometer buffer on both sides. The red indicates areas that are not affected by roads, at least that radius. Now if you go to 2 kilometers, there's very little left. So what I would argue is that these areas, this is the Great Swamp, this is Big River, this is the Situate Reservoir watershed, and these other Buck Hill, these other parcels are absolutely crucial to the preservation of biodiversity, because those are the areas where the road effects are expected to be minimal or non-existent. So if you're trying to protect examples of everything, then you need to protect areas like this. Probably a 1.5 kilometer buffer would have looked better, because it looks like there's nothing left. Actually, you've got pretty good chunks of habitat still left in here, Alton Jones and Arcadia, and it's probably not as bad as I've depicted it there. Let's see. Again, the conservation opportunity. So you have the ancestral biodiversity is strong. There's less happened to it, and there's better conservation opportunity in this watershed because of the parcels of land that remain. these are lichens, particularly a genus I want to discuss called the genus Usnea, which is colloquially known as beard lichen. In parts of the Pacific Northwest, like this picture here in Oregon, Usnea tends to festoon off trees. It's a very showy and dominant feature of moist forests. We have about 10 species in Rhode Island. They all kind of look the same. But if you look at a map of the Usnea diversity in the state, so this graphic here was just generated by point sampling, and it's just a gradient of color that shows the deeper reds are places where there's more different species, not necessarily greater coverage, but just more species. So the reds indicate places where the Usnea diversity is particularly rich, and the whites are areas where it's absent or very poorly represented. Anybody know what creates this pattern? Any thoughts about that? It's air quality. Air quality, because Usnea tends to be very sensitive to airborne pollutants, especially sulfur dioxide. And if you look at a map of Connecticut with a similar approach, you'll see that this part of Connecticut also has better lichen species richness than elsewhere in the state. There's many, many lichen groups that follow this pattern. Usnea is among the most dramatic, but there's tons of other lichens that are sensitive to air pollution. So what I would argue from this is there's a number of ways to measure forest health, and you can talk to Jay Aaron about this because I'm sure he knows all about it. But one way to do it is to use lichens as air quality indicators, which has been done quite a bit in Europe. But what it points out is, to me, these areas, these forest habitats have been less affected by air quality degradation than other parts of the state. So you put this all together for the conclusion is that the Pawcatuck Watershed has the most stuff, probably had the most stuff to start off with. It's a post-glacial pathway. It had a lot of stuff get in there. It's got more biodiversity than other parts of the state. There's been less subsequent trauma from human activity to this part of the state than there is some other parts of the state for a lot of reasons. Road density I mentioned, impermeable surface, you name it. And because of a lot of conservation land already in this part of the state, it has the best conservation potential to promote or at least sustain biodiversity in the state. So you guys got your work cut out for you. And here's the bad news. This is, I call this, very humbly, I call this Reithel's corollary. So, you probably have seen you've probably seen images, the lion lays down with the lamb, right? We all want to believe that there's some interspersion of humans and wildlife where everybody can get along. It doesn't go like that. This is basically what you get. When you add people to wildlife populations, you don't get this interdigitation of wildlife and people, you get people, because the wildlife can't tolerate that. So the trick for many species to maintaining biodiversity is to not eliminate human use, which would, in my opinion, might be is not practical, even if it was desirable, but to be smart about where you focus it, because people are predictable in terms of where they'll go and what they'll do. So by techniques like siting trails or providing parking areas and stuff, you can sort of get people to go where you want them to go. And at the same time, the other side of that coin is there should be areas left alone where people were not formally excluded, but in other words, you don't want to make it easy for everybody to get everywhere. If you do that, you'll have this. And the wildlife and the other species that you're supposed to be protecting here, at least I think that's what you're supposed to be doing in part, will not be there anymore. And the disturbances in people, it's not necessarily a person walking through the forest is not a whole lot different than a deer walking through the forest, so it just comes down to volume and infrastructure. Because deer don't drive cars and drive mountain bikes and stuff, so you just have to be smart about this. So you have your work cut out for you here in the Pawcatuck, because it's a very popular area. It's very popular to promote outdoor recreation. You're probably doing it yourselves, and that's not incompatible, but you have to be smart about how that goes. So otherwise, you're just going to end up with a place that looks nice and will have trees, and some stuff will persist there, but a lot of stuff will not. So that's all I have.